Hello everyone, my name is Xiaoyang Zhang and I am a PhD student from Institute of Computing Technology, Chinese Academy of Sciences. I am very glad to talk about our work, I/O law bounds for auto-tuning of convolutions in CNNs. This is a joint work with Associate Professor Junmin Xiao and Professor Guangming Tan. And our talk is divided into 5 parts. And first of all, we introduce the background and the motivation of our work. The convolutional neural networks are commonly applied to numerous computer vision and machine learning applications, such as auto-drive, language translator, face recognition, and voice assistant. Deep learning gives this era with the magical power of intelligence. However, all these intelligence applications require high immediacy. This makes the industry need to find ways to accelerate the performance of these applications on different hardware terminals, and that's what we can send. In convolutional neural networks, the most important operation is the convolution. The convolution takes up the most time as this figure shows, and at least 70% for CNNs. And the time cost of convolution can be close to 90% for VGG16 at most. Hence, accelerate the convolution operation is the key to improve the CNN performance. And the convolution operation is simple mathematical and it provides a way of multiplying together two arrays of numbers, generally of different sizes, but of the same dimensionality, to produce a third array of number of the same dimensionality. And different filter will give a different feature in CNNs. For CNN operation, for convolution operation in CNNs, there are many different algorithms. Totally speaking, the algorithm can be divided into two classes, the direct method and the indirect method. So there are different convolution algorithms. They all have the same problem, that is, how to make the convolution faster. NVIDIA has also optimized the convolution based on its own GPUs. But as you can see, the convolution performance is still hard to reach the peak performance, not even more than 50%. And as hardware changes and more types of convolution emerge, the cost of optimizing convolutions on each generation of GPUs increase too. Hence, it is necessary to do a further research on how to make the convolution faster. A lot of research have been done on these questions in the past, and PPOP19 provides a two-phase framework to balance the tiling and batching size. It got the 1.4 times performance speed up on average over the state-of-the-art technique. And PPOP20 optimized the batched winograd convolution at instruction level. The improvement of speed is obvious. NVIDIA GPUs are a typical deep learning computing platform. The figure shows the 5 generations offline model. We can find that peak GFlops has increased faster than peak memory bandwidth, and the competitions require high operational intensity to avoid being memory bandwidth bound. On the other hand, as the figure shows, the computation is not sensitive to some optimization techniques such as tile, but the date movement is sensitive to this technique. Therefore, we should figure out how to achieve a lower cache miss and what is the lowest achievable data movement cost among all possible equivalent variants of a computation. To minimize the possible data movement, the lower bound on data movement is needed to be developed. In 1981, Hong and Kang proposed the red-blue pepper game, which is a classical I/O analysis model. It has been proved that it is a very useful model for analyzing I/O behavior. However, for convolution computation, it usually has several stages, each of which involves different computation pattern. The original red-blue pepper game is not suitable for analyzing any multi-stage computation. Hence, the theory is need to be further developed. So the motivation of our work is as follows. For theory, first, we developed the recent I/O lower bound for any composite algorithm, which is typically construct from a number of sub-computations and the red-blue pepper game. And then we establish I/O lower bound result for two main convolution algorithms CNNs, which are direct convolution and the Winograd convolution. Then we proposed some method like we designed near I/O optimal strategies respectively for the direct convolution and Winograd algorithm. Then we proposed an auto-tuning engine to achieve the optimal implementations of our designs. Now, let's start with our work from the lower bound. The red-blue pepper game built a deck, and the I/O means the blue peppers are loaded as red peppers, or the red peppers are stored as the blue peppers. We use the blue peppers as state stored in slow storage, and the number of blue peppers is unlimited, which means that the slow storage is large enough, and the red peppers are used as the fast storage and it is limited. For an algorithm, all input dates are blue peppers at the beginning of the game, and only if all the dependents are red peppers, the computation can continue and the successor can get the red pepper. Another rule is for free operation, and if the data is unnecessary to store in slow storage, it can be free without any I/O. Well, here is an example for the red-blue pepper game. We assumed that the number of the red pepper is 4, which is limited. And at first, all input have blue peppers at the beginning of the game. If we want to calculate this blank pepper, we need to load this blue pepper and this blue pepper as red peppers, like this. Then the successor can be calculated and the result is stored as red pepper. If the red pepper are run out like this, we should freeze some red peppers without I/O or store the red pepper as blue pepper with I/O operations like this. And then this pepper can be calculated and it will be stored as red pepper. So this is the red-blue pepper game. However, if we analyze the multi-stage algorithm with the original red-blue pepper game, for each stage of the algorithm, the output of each stage needs to be stored as blue peppers for the next stage. And in this way, too many redundant I/O operations can be added. Therefore, we should re-exploration the original red-blue pepper game to avoid the redundant I operations for multi-stage algorithms. First of all, it is not easy for a composite algorithm to deduce the value of PS indeed. While we could try to get a valid lower bound of PS representing as HS, and the Q can be get through HS. And we use this figure as an example. Assume that K is the number of vertices in dominator set D, and K1 is the number of the vertices in dominant set for stage 1, and K2 is the number of vertices in dominant set for stage 2. And phi 1k is the maximum of vertices generated by stage 1 with K1 input vertex, and perceive 1k is the maximum vertex generated by stage 1 but used in the next stage. And similarity, phi 2k is the maximum of vertex generated by stage 2 with k2 input vertex. And then, in this way, the number of vi can be got as follows. Well, so for any k and vertex set U with any dominant set D, define two vertex generation functions for the J sub-computations as follows. And we can get phi J tilde and prosthetic tilde. Then we define the maximum vertex generation function as follows. It is clear that phi j k and the percentage k provides the upbound estimation on the number of vertices in uj and oj tilde. And after getting phi j and percentage, we got ts through theorem 1. ts and substitute ts into q in original red-blue paper game model. Theory 2 can be got, and the detailed proof can be found in our supporting materials. With the theorem 1 and theorem 2, the proof approach of general composite algorithm can be described as three steps. The step 1 is to estimate the total number of vertices V in deck G VE of a composite algorithm. And the second step is for a G stamp in the multi-stampation of G. Estimate phi j and psi j respectively. Based on equation of Ts, compute the value of Ts. The third step is by equation of Q mentioned above that use IO lower bound. And we can get the lower bound of direct correlation and the Winograd algorithm through the proof approach. And for direct correlation, there are two steps. The first step is to generate W curl H curl C terms by executing the corresponding element product of II with Kj. And the second step is to sum the product terms generated by II and Kj. Then we can get the number of V. And donated R as the maximum real number of each input in an input image by different sliding window. For the two step in the direct correlation, we can prove the value of phi 1, phi 2, and psi 1. Once phi 1, phi 2, and psi 1 are got, the Ts can be got by theorem 1. Then we can get the lower bound of direct correlation with the value of Ts by theorem 2. In similarity, the lower bound for Winograd algorithm can be got through the deck shown on the left. The Winograd algorithm is divided into four steps, and the first step is transformed matrix multiplication, and the second step is an element-wise multiplication, and the third step is element-wise addition, and the final step is transform the matrix multiplication. And first we can get the number of V like this, and then we can get the phi I and psi I through the left deck, and Ts can be got through theorem 1. And then we can get the lower bound of the Winograd algorithm like the direct correlation with the value of Ts by theorem 2. And with the lower bound, we can design the strategy for the direct correlation and Winograd algorithm. In the proposed general I/O lower bound theorem, the highest order term in I/O lower bound result must be determined by some phi j. Specifically, for the direct correlation, the maximum vertex generation function phi 2 for the last step determines the highest order term in I/O lower bound. Therefore, the output date should be focused on firstly, and its reuse should be prior than the input date reuse. And then we divide the input date into many sub-blocks. For each x, y, z sub-block, which can be fed into fast memory, we select the x prime and y prime along the channel direction. We should decide the value of x, y, z to maximize the output date reuse. The reading date is as follows, and it is easy to find when x, y is equal to rz. It is easy to be minimized, and the write date is equal to h out, w out, c out. And in this situation, the strategy can reach I/O lower bound of direct correlation. Similar to the analysis of direct correlation for Winograd algorithm, the highest order term in I/O lower bound comes from phi 3 for the third step, rather than phi 4 for the last step. And then we can get reading date and writing date. And it's easy to know that when xy is equal to r squared z, the strategy can reach I/O lower bound of Winograd algorithm. And then we simply introduce the auto-tuning process. It is easy to understand the auto-tuning process. We design the template with near I/O optimal strategy, and we can get some random configurations with the template. The model can be trained with a dataset and get a cost model by the machine learning method. Then the cost model helps us to explore the better configuration. And finally, the new information will be updated to dataset. And in this way, the best configuration which constraint with our strategy can be found. The configuration explorer contains two parts, searching domain and searching process. And the searching domain is designed by the right table to adjust the appreciated size of S according to the actual situation. And the searching process is a parallel searching process to select configurations from the searching domain. Now let's talk about our experiment result. And first, we compare the performance with QDN, and we can find that the benefit from the strategy is consistent as the H in and W increase. And the strategy benefits decrease as the stride mu increase. And the strategy contribution is higher for the direct correlation with small c out. Winograd algorithm is just the opposite. And the strategy is always works well with getting the batch size. And our I/O optimal strategy implementations can achieve 3.32 times performance speed up on average, and it still achieves 1.51 times performance speed up on average compared with scaling the batch size of QDN. And then we compare the different automation methods, and each automation method gradually finds the better configuration with higher float point arithmetic efficiency. But the auto-tuning engine can find better configuration much faster than others, and the proposed searching domain and the effective parallel searching method in the design of the auto-tuning engine is used for template generation. Then we compare the auto-tuning engine with TVM, and auto-tuning engine reduce the size of the configuration space, and the auto-tuning engine finds the final solution due to the faster due to the proposed searching domain. And the final configuration found by the auto-tuning engine usually has a shorter runtime than the best solution in TVM. And we also make a performance comparison on CNN models. We find that our optimal implementation can achieve a performance speed up compared with using cuDNN on SqueezeNet, VGG, ResNet, and Inception v3. As for different generation of GPUs, the strategy can always work well as these figures show. Where totally speaking, our work makes the following contributions. First, we developed the recent I/O lower bound theory for any composite algorithm first, and it is a general theory for multi-stage algorithms. And then we established the I/O lower bound result for direct correlation and Winograd algorithm. And with the I/O lower bound result, we designed a near I/O optimal strategy for the direct correlation and Winograd algorithm. And finally, we proposed an auto-tuning engine to achieve the optimal implementations through our near I/O optimal strategy. And this is our work. And thanks for listening.